Okay, I'm hoping we can finish up chapter 14 today. What we're going to talk about today is activation energy. And I used to have you calculate it, but I'm going to show you why I'm not going to have you do that anymore. It's kind of a complicated. You have all the materials, but the actual solving it is it's more of a calculus problem. So, and again, I'll show you. I just want you to know really understand what activation energy is. And again, it's energy you need to get a reaction started. Okay, the minimum amount of energy needed. Okay, for a reaction to start is called activation energy. It's energy that activates a reaction. There's a barrier for you to overcome. Here, the barrier they're showing, like this guy is going to putt. If he wants to get here, he has to overcome this little hill before the reaction gets going. So we're going to say this is the reaction. If he doesn't overcome this, it's not going to get on this side. It's going to come right back to him. So in order for a reaction to start, you have to make sure you have enough energy to overcome the barrier, and that's activation energy. Okay. They have transition states. They gain energy as the reaction proceeds until the particles reach like maximum. They're moving around as fast as they can and they're banging in, their collisions are going. So when they get to that point, there's a peak and then it goes back down again. So it depends on the organization of the atoms. We've talked about that a little bit before. They have a state that they need to be in, and the best state as far as phases is gases, because then they're moving around more. But when they get to a certain point, you'll see a curve for activation energy. I'll just show it to you. Okay. But there is a phase or an amount of energy that needs to be added before a reaction starts. And again, that's activation. Here's what I was talking about. Okay. This is, what we need to get over. And this is the complex. This is where it starts. So from the initial to up to this peak, that's the activation energy. Okay. And again, in this reaction, it's showing a reaction where we're forming bonds and breaking bonds, and they're taking this and they're breaking the bonds and making a different substance. So again, we need this E sub A is activation energy. This is the energy required to get this reaction going. Okay, it's the highest energy state up here. And if you want to calculate it, there is a formula. I'm going to show it to you. But again, I just decided that it's not that important that you know how to find this number. It's more important that you understand what it is. Okay. And when you have a reaction, it doesn't matter. Activation energy occurs whether it's an endothermic or an exothermic, whether it gives off heat like an exo or it absorbs heat like an endo. It doesn't matter. They all need any reaction. Sometimes it's a little amount, and that's going to happen right away. Sometimes it's a heavy duty amount, and that's going to be a slow reaction. And if it's too high, it would be a non-spontaneous. In other words, if you don't add energy, it's not going to happen. Okay. So the rate constant is a magnitude of this E sub A. That's what, determines it. Okay. So how do we get that? Well, again, we talked about this before. Gases have more of their own energy. So they have a lower activation energy than if you have like liquids or solids. Okay. So if you have high energy, you have to have more molecules. In other words, you're going to have to increase the concentration maybe for the reaction to occur. Here you can see activation energies. A larger fraction of the molecules are going to react at a higher temperature than at a lower temperature. And again, that's because they're moving around faster. They're bashing into each other more. Okay, here's the formula for actually figuring out activation energy. Okay, so if you want to figure it out, you have to take the inverse of the constant for one reaction. That's what we did last part of this. First, you have to take the constant for the first reaction, and you have to divide the constant for the second reaction, and then take the inverse of that. And then you need to use R, which is the gas constant, and you have to use the inverse of the second temperature over the inverse of the first temperature. And this is a lot. Okay. And like I said, you spend more time worried about solving this and actually figuring out what it is. So we're going to pass on that. Okay. Here's a chart to figure out activation energy. Here's the Ks. If I wanted to really plug them in, let me show it to you. Okay. Here's the formula for finding it. Okay. R, and now when we did gas constant before, it was 0.00821. This one is in a different unit. Okay. This is in, I think it's torr. or millimeters of mercury, which are the same, instead of atmosphere. So it's a little bit different number, but this is the number you would always use. Okay. But if I want to solve it, first thing I got to do is I got to change my temperatures. Like back here, the temperatures were in Celsius, so I got to change them to Kelvin. Okay. And then I'm going to substitute numbers in. Okay. The inverse of, here's K sub 1 and the K sub 2. So I throw them in there. And then I have to take those numbers and I have to divide by the gas constant. And then these are the inverse of the various temperatures. And again, it's a big crazy number. And to solve it, sometimes it's a lot of work. So instead, I just want you to understand more about what activation energy, and we're going to kind of skip over. I'm not going to have you do activation energy. I used to, but the more I thought about it, it just really confused everybody. And I don't really know that it had a purpose, because I don't really care if you can do advanced calculus problems. I want you to understand the chemistry of it. And so that's why we're not going to do these problems. But again, when you did all this and solved all that and plugged everything in, this is what you would have got. So this is the activation energy for that problem. Okay. So what does it mean? That's more important to me. Okay. Activation energy is related to the rate of the reaction. So if the rate is higher, then the activation energy is lower. Okay. The higher the activation energy. So if it takes a lot to get it rolling, then the rate is going to be slower. Okay. If the activation energy is low, then the reaction is going to happen faster. So if you don't have to add a lot of energy to get it rolling, then the chemical reaction is going to occur faster. And there's a level, I'll have to look it up. I think if it's a negative number, that's a non-spontaneous reaction. And if it's a positive number, it will happen sometimes slowly, and sometimes fast. But if you have a low activation energy, if it's not a very high number, then you're going to have a faster chemical reaction occurring. In the case, the rates are going to be much faster. Okay, so what limits the rate at which it occurs? Well, the overall reaction of anything can only occur as fast as the slowest mechanism. Okay, that's kind of like that phrase, you're only as good as your weakest link. Well, if you look here we got cars going, and they can only get through, I think, one part here. They can only get through this lane here or something. And so what happens is this rate, this step slows it down. So even though this, they can zip right through here, because it takes a while to get through here, this slows your whole thing down. Over here, we've got, we got cars are slowed down at A. So A is what determines the rate, because this is the slowest step. Here, they can't get through B. So A doesn't determine its, and again, we're going to relate these to like K's, they're constant. B is going to be the one that determines the activation energy, because this is the slowest step. Okay, so whenever you're trying to figure out activation energy, there can be many steps to it, but the step that's the slowest is that's the one that determines the rate. Okay. Another thing we talked about a little bit about was catalysts. Catalyst can increase the rate of reaction. And usually what a catalyst does is lower the activation energy. That's how it gets a reaction to occur. In your body, you have many enzymes. Okay. Enzymes really control reactions that occur in your body. They can start them, they can stop them, they can speed them up, they can slow them down. They're all organic or biological, if you want to call it, catalysts. Their job is they increase the rate of reaction by decreasing activation energy. In your body, you have some that decrease, so they can do all of them. But really, when you have a catalyst, what happens is it changes the activation energy. And so reactions that happen faster, and what they can do as well or the catalyst itself isn't changed. So you can use it over and over and over and over and over. Okay. Catalysts change the mechanism. Okay. So if you look here you have a normal reaction. This is hydrogen peroxide with bromine, and up it goes and whatever. And this is your activation energy right here. Well, we add a catalyst and it's much lower. So the reaction is going to happen faster. Okay. That's really what a catalyst does, is it changes the activation energy. We have, 3 different types. Homogeneous means it's in the same phase. as the whatever's being reacted together. Heterogeneous, you can have different phases. And then you have enzymes, and I talked about enzymes a little bit too. Enzymes are biological catalysts, okay? Here's an example. If your reactant and your catalyst are in the same phase, then the reaction is going to happen faster. It'll lower the activation energy. This is where we got water, and then we add sodium bromide to it. And then you can see it changes the reaction because they're both liquids, okay? If you have reactants and catalysts dissolve in the same solvent, okay, then again, these are actually dissolved in water. They're both aqueous solutions. So because they're both in the same phase, reaction happens. It lowers activation energy and the reaction happens faster. If they're not in the same phase, okay, if they're in different phases, usually what you'll have is a gas that's passed over a solid. That's probably the most common, but it doesn't occur as fast, okay? So if you have a heterogeneous catalyst, it's not going to happen as fast as if you have one in the same phase in a homogeneous, okay? So again, you're going to get more steps to this one. And remember, the one that's the slowest is the one that determines your overall rate. Okay, and then there's enzymes. Enzymes are biological catalysts. Like I said, we have thousands of them in our body. Okay, here's an example. If you take liver, I don't know if any of you guys get a cow, a butchered cow, or buy half cow or whatever, you'll get liver usually. If you grind it up, there's a catalyst in it. It's called catalase, and what it does is it converts hydrogen peroxide to oxygen. So if you put a little bit of this into water, just and it fizzes and bubbles. It's kind of cool actually. But there's regions on the reactants. They attach. On an enzyme, you have a special area. Every enzyme is very specific. Okay, it's not like you have an enzyme that affects, like if you're using enzymes to break down your food, to break down a hamburger, you might need 20 different enzymes, because it isn't like one enzyme will break down 6 different things. They're very specific. They only do one at a time, and they only do one thing. So because they have an active site, and then whatever they react with is called a substrate. So if you have an enzyme with an active site, and let's say it reacts with starch, you have enzymes that break down starch. Well, its substrate would be starch, or a substrate could be another food molecule, or a substrate could be a muscle, or a substrate could be a gland. Okay, substrate is whatever the enzyme reacts on, and they have a specific site that they act on. Okay, here shows you what happens. Okay, here's my enzyme, and it's going to act on whatever the substrate is. Like I said, this could be an organic molecule, it could be an organ, it could be, the enzyme could be some type of hormone, whatever. Okay, so this site, they have to match up. If they don't match up, they don't work. So what will happen is the enzyme will come in and it'll attach to the substrate, and then the reaction will occur. And when it's done, you'll get 2 new products. But you notice the enzyme's still the same. Okay. Again, a catalyst works on the reaction, but it doesn't change itself. So the enzyme changes the substrate. So there's a reaction that occurs, and you get these products, whatever they may be. But the enzyme itself stays the same. So it can be used over and over and over again. Here's a fancy organic molecule, but here's my active site right here. The active site has to attach in the substrate. That's where it's all going to happen. Then a reaction is going to occur, and maybe this will split into 2 or 5 or 10 or whatever. But this is called the lock and key. Okay, they fit together, and then a reaction occurs. But again, your key is still the same. You can be used over and over and over again. Okay, so in an enzyme substrate model, the substrate fits into the active site of, this fits in here. This is the active site. This is the substrate. You got something going on, you got a reaction, and then it happens. So that's how an enzyme would be a catalyst. And they call it the lock and key, because the key, the lock, they fit together, and then the reaction occurs. And I think that's it. Okay, like I said before, enzymes are very, very specific. For every reaction that occurs in your body, you'll have different enzymes. You have thousands of different enzymes. Okay, and I think we're done. Yes, we are. Okay, so we're done with chapter 14.